Okay, welcome back. I think I cannot place the F10 to single step through it, so I need to use the simulator single step through it. Okay. Otherwise, it actually stop recording. Okay. So now if I single step through the first instruction, I set the T2 to DC0. That's correct. And then now I go here and then single step through it. Oh, actually here there's a single step through here. A single step. Okay. So now the T2 is DC0, and then one more, the T1 will be 3 DC0. So let's get back check. Is that 3 DC0? Yeah, that's 3, that's D, that's C, that's 0. Okay, so that's the result. The result is correct after we over T1 and T2 put the result to the T0, and that's that. So the program is running. Okay, that's old operation. Okay, so you should try yourself, okay, for these test programs. Now the NOT operation, instead of say NOT, we use NOR, nor, okay, nor instruction, okay. So again, if we nor T1 with T0, okay, so that will, the T1 if T1 is this number, right? So it's actually doing the not A or B. Okay, so so it actually, if you put a 0 here, A or B will be just T1, right? And then the negation of T1 will be everything change from 1 to 0, and then 0 to 1. So 0 to 1, 1, 1, and then it's negated. Okay, so the MIPS has this NOR 3 operand instruction. So if you want to do a NOT, you can actually use a 0 operator, a 0 operand, okay, with this T1. So it essentially doing a negation operation, okay. So it's doing the A or B. So what if you have the some non-zero number here? So it will actually do the A or B first and then negate it, okay. Conditional operations. So branch 2 will label the instruction if a condition is true, otherwise continue sequentially. So we use a label to indicate the instruction address or target address for a branch. So branch is used to implement if then else the kind of decision structure or the loop structure. Okay. So for example, there's a branch equal, BEQ stands for branch equal. So if branch to the L1 if R is equal to RT. Okay. So L1 is a label. So the label is specified. That's the main column. Like the main column is a label here. The main column here, that's a label. So normally we put a label to the first column, followed by the second column, that's the OP code, and then followed by one or more operands, and then the last column, this area will be the comment. So for example, you can put a comment start with a pound sign. So this is set T2 to this number DC0. Okay, so that's the comment. Okay, so the first column always labels, then the second column the OP code, like an end, old. These are the OP code, or mnemonics, instruction name, and then followed by the operands separated by the comma, and it's called the command separated list operands, and then followed by the last column will be the comment. Okay, comments. So here we want to jump to L1 based on condition if the RS is equal to RT. Okay, so we use this to make a decision, to change the flow of the program. So we can actually change the control flow based on the values stored in the RS and RT. BNE, BNE stands for the branch not equal. So we jump to L1 as long as the RS is not equal to RT. Okay, and then the JL1 is unconditional jump. No matter what, you just come here and then you will jump to the L1. Okay. So here is the C code for the if then else structure. So if I equal to J, then F is G plus H. Else F is G minus H. So F is based on the condition I equal to J. If that's the case, then F is the sum of G and H. If I is not equal to J, that's this branch. Else case, that's F will be the difference of G and H. Okay, G minus H. Okay. So if we compile this C if decision structure to the MIPS code, that will be this code. So it's BNE S3, S4. So we assume S3 stores I, S4 stores the value J. Okay. So if I is not equal to J, we jump to else part. Okay. Then we do the subtraction. This S0 store G. Store the value of F, and then S1 store the value G, S2 store the value H. So S2 minus S1 the value put into S1. Okay, and then on the other side, the then part, if you don't jump, that means S3 is equal to S4. In that case, we want to do the sum of GH. So here we have add instruction here, add S0, S1, S2. Okay. So now let's use the spin to simulate this. Okay. So first we put some value to S3, S4. Okay. And S1, S2. So let's do S1, S2, S3. Let's do 3, and then this will be 2. Let's set some value to it. Okay. And Li S4. Okay. Okay. So we have the value S1, 2, 3, 4. It's 1, 2, 3, 4. Okay. Then we first have BNE branch. Okay. Condition that check S3, S4, S3 and S4, and then jump to else. Okay, else. Then this will be the if part. Okay. And then after if part, we have a jump instruction to end. Right. Exit. Okay, we use exit. Okay. And then this will be the else part. Okay. Then that's the. Okay. So these are labels, and I don't need this. So here the if part, what do? We actually do add. Add the S0, 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 and then S1, and then S2. Okay. Then in the else part, we do the subtraction S0, S1, and S2. So what will be the result after we run this piece of program? What will be the value stored in S0? What do you guess? So here to answer this question, we have to find out the values stored in S3 and S4. So is S3 equal to S4? No. So the BNE will jump because S3 is not equal to S4. You will jump to else. So the S0 is calculated by S1 minus S2. So S1 is 1, S2 is 2, so 1 minus 2 is -1. So S0 should be -1 after we run this piece of code. So let's save it and then load it to the PC spin and then find out. Okay. Okay, and we set the breakpoint to the jump and link command. Okay, set breakpoint and run it. Okay. So now we set 1 to S1. Okay, so S1 now is 1. Okay, now S2 is 2, S3 is 3, S4 set to 4. Okay, now it go to the BNE branch not equal. So if you jump to the else, where's else? Else is here. Okay, else here. So let's see, you jump there. Yes, it did. So sub S16, S17, and 18. So it run it. So now we got the S0, FF, and do you remember that OF? The number with OF, that's the -1. Okay, that's a -1. Okay, that concludes this example and the question. Well, okay, so if questions, post their question on the discussion forum. Okay. So now after that we know this. Okay. And there are other ways to implement if then else. So you can think about, is there any way you can do that? Use the BEQ instead of BNE. Okay, if you use BEQ, how do you do? Okay, so think about how to do that and then write a test program to implement the if then else using BEQ instead of BNE. Okay, so the C code now here we're going to take a look at the loop statement. Here we have a while loop. So you set I equal to K. If that's the case, then you add the I to 1. We can actually increase I by 1. Okay, increase I by 1 is plus equal 1. So in this loop, we're gonna count, how many values stored in the self array that has the value k. Okay, so that's the loop. So let's say I in S3. We set I in S3 and k is in S5. And the address of the self, this is array. Okay, it's in S6. So first we have a shift def to logic T1. Okay, and T1 is the value after we shift left S3 by 2. So S3 is the value of I. Okay, then if every time you shift that twice, that means you times its value by 4. Okay, so that's because that we want the address to increase by 4. Okay, so after that you add the T1 S6 into the T1. Okay, so now the T1 S6 is the address of the safe. So if we add T1 to the S3, you will calculate the offset of the element you're going to access. Then the actual address is in the T1. So after that, you use the T1 as the base address, the offset 0, then you can load the value at that element to the T0. Okay. Then after you load the element to the T0, then you can compare that value to K. So you can compare to the K value stored in S5. If not equal, you do exit. Otherwise, you add the S3, which serves as a counter by 1. And then after that, you loop back to the beginning. Okay. So that will, serve, that will actually implement the while loop that find the number of elements saved in the safe array that has a value k. Okay, so I'll stop here. Then see you next time. Okay. Hi everyone. My name is Dan Low. So today I want to keep talking about the MIPS 2000 assembly programming and the MIPS 2000 architecture and instructions. So, so first, how do we represent instructions? And or another say is that how do we encode instruction so the CPU knows what to do? Okay, so instruction will be sent to CPU. Then CPU will execute instruction based on the data stored in the instruction. And as the last time we talked about the length of instruction in MIPS 2000 is 4 bytes. So we're gonna take a close look at the 4-byte instruction content. So instructions are encoded in binary. So it's either 0101. There are 32 0 or 1s. It's called machine code. A mixed instruction is encoded as 32-bit instruction with no exception. All the instructions have the 32-bit length. Okay, and small number of formats encoding operation code, register numbers. So it's regular. Okay. So the register numbers from 0 to 31, from the register number 8 to 15, that represent the T0 to T7, and T stands for temporary storage. And the T8, T9 are register 24 to 25. So altogether you have 10 temporary registers. Then the S0 to S7 are registers, from the number 16 to 23. So S stands for saved. So sometimes we need, well, basically you can use these 32 registers, at your whatever you like. However, we name it this way. So when you say S0, means this is saved register. So sometimes you, if you want to use that, you need to save the registers. However, the temporary registers, you can use it without any, without worrying about whether somebody will use that in later or before. Okay. However, the save register is just convention for writing the assembly programs. But if you follow the convention, your code will be readable, more readable. Although you can use any registers at any way you like. Okay. So here's the MSB R format instructions. I think we have looked at this before. So the LB code is 6 bits, 5 bits for R's, and RT 5 bits, RD 5 bits. The shield amount 5 bits, and the function code 6. Okay. So this R-type example instruction is like add instruction. It's R-type. The R stands for the registers. That means all the operands are from registers. So T1, S1, S2, they are registers. So they provide the operands for the add instruction to operate upon. So if you put the 0, that's all because 0. The function call for the add is 32, 17, 18, 8. That represent the register numbers. Then these combined together, this will be the instruction. This will be the instruction for this add S1, S2, and put the result to the T0. Then sometimes if you see this binary representation is not really convenient, so we normally put the representation into the hexadecimal. So in order for you to convert the binary to hexadecimal, basically you need to group from the right hand side 4 bits at a time, 4 bits a group, all the way to the left. So you got 8 groups. So each group then converted based on this table from the 0 to 15, and then be careful that the number larger than 9, 10, number than 9, the A is represent 10, B is for 11, and C is 12, D is 13, E is 14, and F is 15. Okay, so that's the convention. It is lower cases or upper cases doesn't matter. Okay. Now let's take a look at the I format. In the I format, basically, you reserve the constant or address area from the instruction. From the instruction. So basically, the instruction, the total is half of the bits are used for constant and address. This 16 out of 32, half. Okay, and then there's a 10 bits, one for 5 bit RS, the source register, and the target register 5 bits, and OP equals 6 bits. Okay, so so basically the constant range will be negative 2 to the 15 to 2 to the 15 minus 1. Okay, then the address, sometimes we just recode the offset, so that will have to add it to the base address in the RS. Okay, so the design principle here is a good design demands a good compromise. Different formats complicate decoding, but allow the third loop instruction uniformly. Okay, and keep the formats as simple as similar as possible. That's the goal. That's design goal. So that's good design demands a good compromise. Okay. So here On the stored program computers, basically invented by Newman. The first computer, the ENIAC and ZIC, invented by two professors in UPenn. Unfortunately, that computer cannot store a program. So after about 1 or 2 years later, von Neumann, proposed the concept of stored program computers. So stored program computer basically the programs are stored in program memory, non-program memory, program memory of the computer, and that is the processor. So this memory will store the data, the code of the machine code of the program, and anything else. Okay, so the processor will execute the store program. Okay, in this way. So basically, instructions represent in binary just like data. So some basically this memory also keep the data. Okay, keep the data. So accounting information, machine code, and then the payroll data. See the data here, and then the book text. Okay, the data, and then source code in C editor. And the instructions and data stored in memory as well. So before you can run a program, the program had to be loaded from the hard drive to memory. Okay, and programs can operate on programs. Okay, so compilers, linkers, they are programs that will work on your programs. And binary compatibility allows compiled programs to work on different computers. So if you have standardized ISA, okay, then binary compatibility allows the compiled program to work on different computers, as long as the different computers knows how to deal with the instruction. Okay, it defined in ISA. So now let's take a look at logical operators. Instructions for bitwise manipulations. So bitwise means the instruction will operate on the operand based on a bit basis. So for example, the shift depth. Okay, in C use less than. This operator will shift left 1 bit of the operand. In the MIPS, we use SLL. That stands for shift left logic. Similarly, we can have shift right 1 bit logic is shift right logic SRL. And bitwise AND, like AND or NI. So the NI, anything followed by any instruction name followed by I represent the immediate addressing. That means this instruction will come with a 16-bit immediate value, and this AND will be the the register R type instruction. So all the operands are in registers. And bitwise OR or ORI, and ORI is the immediate addressing version of the OR instruction, and the bitwise NOR. So we have NO NOT, NO NOT, NOR. NOR is NOR, so it stands for the NOT instruction. So that's flip all the bits in an operand. So this is useful for extracting and inserting group of bits in a word. If you want to insert something to a word, you can use OR. Okay, you can insert it to it, and you can extract it using AND operation. Okay, so that will get something out. Okay. Shift operations. Now shift operation instruction has this format: the shift bit, OP code, and then RS, RT, RD. Each of which contains 5 bits, and then shift among 5 bits, and then a function called shift bits. The shift amount depends on how many positions to shift. So you can shift to the 5, which is 32. Okay. 2 to the 5 minus 1, sorry, 31 bits. Okay, because 5 bit can represent 0 to 31. Okay. And the shift depth logic, the shift depth and shift when you shift the operand to the left, the rightmost will be 0. Okay, the rightmost will feed in the 0. Similarly, if you shift depth by I bits, it's similar. In math, it's equivalent to the multiplies by 2 to the I. If you shift left 1 bit, that means multiplied by 2. If you shift left 2 bits, then multiply by 4. If you shift the 3 bits, that's similar to multiply by 8. Okay. Shift right logic, shift right and filled with zeros. So when you shift right an operand, the leftmost will be filled in 0. Okay, so if you shift right 1 bit, that is equivalent to divided by 2. Okay, if you shift right 2 bits, now equivalent to divided by 4. Shift right 3 bits, now equivalent to divided by 8, and so forth. Okay, and this is for the unsigned only, because it does when you shift right 1 bit, if the leftmost bit is 1, and that's negative, right? Then if you shift right, then negative becomes positive, and that's not good, not okay. And we'll deal with the sign bits later. So first take a look at the AND operations. This is useful to mask bits in a word. So you can select some bits to clear others to 0. So for example, in this case, the ST2 is this. Okay, there's a 0010 a 0011 here. Okay, and then if T1 is 1111 here, that simply want to mask this out. So only extract these 4 bits out. Okay, that becomes 0011. So we're gonna write a program to do this to test it. Okay, so let's go to here. So now this is some test program here I wrote. Okay, so let's first set the T2 to this this value. Okay, so we use li. Okay, then T2, and then T2, now we're gonna set it to what will be the value. Okay, this value is 0, 0, 0, 0, 0, right? How many zeros? 5 zeros. Okay, so it's 0, 0, 0, 0. Okay, and then this one is 0, 0, 1, 1. That's 3. Sorry, this one's 1, 1, 0, 1. That's 8 plus 4, 12, 12 plus 1, 13. So 13 is D. And then this guy's 1, 1, 0, 0, that's 12. That 12 is C. And then that's 0. Okay. So this is hex. So let's put an H there. Okay. And then let's set a T1 to that number. So Li T1. So it is number 0, 0, 0, 0, and then 3. 0, 0, 0, 0, 3. 0, 0, 0, 0, 3. Okay. And then C00, C00, H. Okay. I think I'm missing the one. 0, 0, 0, 0. Oh, 0. Okay, that's missing a 0 here. 0. Okay. Yeah. And then we're gonna end T1 and T2, and then put a route to T0. Okay, so save it. Now let's go to the Qt spin and load the file. Okay. That's a syntax error. Well, it's simply telling that we cannot. We need to use another use some other constants. Okay. So let's go back to check. How do you give a constant? Here I think we have constant somewhere. Okay. Okay, we can put a constant, but we need to tell what value is this. Okay, so let's put the H first. Okay, H, and then try it. Okay. I think we need to find out how to represent a hex constant. Okay, so Hold on 1 second again. Okay, so I think we cannot use H. It does not take H to represent the hex number, so we put a 0x there. Okay, I represent the hex. Save it, and now we can load it again. Okay. Okay, now we take it. So as usual, let's set a breakpoint on the JAL main here. Okay, so set a breakpoint, and then run the program, and then yes, we're gonna single step through it. So first we're gonna set the T2, right? T2 to 0DC0. Okay, so T2 is right here. T2 is here. Okay, so that's single step through it. So go to the simulator, go to single step over F10. So now T2 got a DC0. Yeah, that's correct. That's what we want, right? DC0. We can, okay, now we put it, we can change that to the binary data. Okay, and now single step through it again to set the T1 to the 3C00. Okay, that's correct. And then after we end the two numbers together, again we go single step through it. Then we got a T0 is a C00. Okay, C00. Let's go back to check the actual result in the slides. Okay. Okay, there we go. So here the result T0 should be 00000, and it is A4 is a C, so it's C00, so it's correct. So the result is correct. So C00 result is correct. Okay, and yeah, you can right click on this one and change it to binary. Then that'll allow you to check binary. So in the binary, this is 32, right? Not there. T0. That's the binary. Okay. So it's 1 1. It only show the non-zero. Yeah, non-zeros. Okay. So it only show up to the leftmost one. Okay. So the best way is you change that to hex. As you can see, that's good about hex representation. Then make it more compact to repeat the number. Okay. So that's the end example. Now let's get back. No, let's keep going. The OR operation, same thing. If you can OR the number together, T1, T2, and then put the result to T0. And here the T1 is actually the same number, right? The same number, that's the 3, or not 3, sorry. That's the A4, 12, 13. So 13 is DC0, right? And then now if we change that, and the T1 is same value as we see. So the only thing we change is to change the end to old. Okay. If we do that and then save it, run it again, what happened? What happened is 1111, this area will change it is 0011 to 1111. So result should be a 3DC0. Okay, so let's check. Okay, no, let's save it and then run it. So I can go file, reinitialize, and then load the file. Open, and then set a breakpoint to the JAL German link main. Okay, set breakpoint and run it. So now single step through it. Okay, now I'm gonna press F10 so you cannot see it, but I actually press X10 to single step through it. Okay, so first we